another big topic that you're going to be able to see in problems in competitive programming, especially in the silver division. So let's take a look at our agenda. So first, we're going to be going over the homework from yesterday that was based on graphs. We'll do an introduction to the problem of why we need prefix sums and how to use them, like their algorithm and implementation. We'll go over more complex versions of prefix sums, like 2D prefix sums, and then go over some example problems. So let's start off with our homework review. Let's read this quick. So this is from the 2016 US Open contest, problem 3 in the silver division. So it's a little more difficult. So Farmer John and his cows are planning to leave town for a long vacation. Farmer John wants to temporarily close the farm to save money in the meantime. The farm consists of N barns connected with M bidirectional paths and between some pairs of barns, and he wants to shut the farm down one at a time for the barns. And when it closes, all the past adjacent ones also close. Farmer John is interested in knowing at each point in time initially after each closing whether his farm is fully connected, meaning that it's possible to travel from any open barn to any other open barn along an appropriate series of paths. Since Farmer John's farm is initially in somewhat a state of disrepair, it may not even start out fully connected. So the first thing to realize in this problem is that it's a graph problem. Usually, like at least from experience, most silver contests always contain at least one graph problem. So in this case, problem 3 is the graph problem in this contest specifically. And the way you realize the graph problem is you start reading words like connections, you start seeing like sometimes you can even tell from the variables, honestly. If you see N and M, that's a pretty common indicator. Not always, but sometimes when you see the variables N and M being used, it can be something like a graph. Bidirectional paths is a big hint to you being know it's a graph. You see the word connected. These are kind of hints that you know that it's going to be a graph problem. So in this graph problem, we can kind of tell what's going to be the nodes and what's going to be the edges, right? So the N barns, these are going to represent the N nodes, and M bidirectional paths are going to represent the edges. So in this input here is telling us that there's nodes 1, 2, 3, and 4, because that's what N is. And there's going to be 3 total paths. So let's draw this graph out. So the first 3 lines are going to be representing the pair of connections that are between the nodes between 1 and N. So there's N nodes, 4 nodes total, 4 nodes. And there's going to be a graph that has these connections. So node 1 is going to be connected to node 2. Node 2 is going to be connected to node 3. And node 3 is going to be connected to node 4, right? That's what is happening between within this graph. These are the connections that are there. So next, what this problem is asking for is originally it's going to ask, is the farm fully connected? So obviously we can see if the farm is fully connected here, but it's possible that it wasn't connected. So let's say we had a graph like this is a separate case than the sample input, but let's say we had a graph like this: node 1, node 2, node 3, node 4, right? These two group of nodes are part of separate components. A component is, if you remember, a group of nodes. So they're part of separate components, meaning the graph isn't fully connected. So that could be the sample input, and then you wouldn't have a fully connected barn in the first place. But over here, in this problem, we are given a fully connected barn initially. As you can see, all the nodes can be reached from like one of them. Wherever you start, you can go to another, right? So that's how you know that they're part of the same component. So it's asking if they're fully connected. So you would print yes first, and that makes sense. So after that, you can kind of just ignore the last input because you're only asking for 3 outputs here. But basically, you're going to close these barns in order, and you're going to have to print you're going to close these barns in order, and you're going to have to check if the graph is still fully connected after each closing. So for example, after the first closing of node 3, we're going to close off node 3. Then you can see that the graph is not fully connected anymore because 1 and 2 are part of its own component and 4 is part of its own component, right? So that's why we're printing no over here. Then we're going to close off 4. So when we close off 4, well, now the graph is fully connected again because there's only nodes 1 and 2. So that's why we're printing yes. And again, once we close off the next node, Let me see, we close off 3, we close off 4, we close off 1 next, and we can see 2 is just by itself. So that's why we're printing yes again. And yeah, that's basically how the problem is formatted. So I'll define an algorithm that we can use to approach this. So again, Silver, most commonly, you're going to see algorithms like depth first search inside your graph problems. Most commonly, that's the algorithm that's going to be used. So essentially, what we're going to do is first, we're going to read in the input of n and m. We're going to construct a graph like this, just as we did earlier. Graphs, you can kind of just make look like whatever, as long as the nodes are connected the right way. But yeah, so this is our graph over here. And we're going to DFS at node 1 originally, and we're going to see if the graph is fully connected. The way we know it's fully connected is there's n nodes, right? So n is equal to 4. If we run a depth first search on any node in this graph, let's say node 1, and the total amount of nodes we visit is equal to n, that means we visited all the nodes that we're supposed to visit, and the graph is fully connected, right? So that's the logic behind that. So that's how we can tell if it's originally going to be a fully connected graph. So if we want to tell after each closing, here's what we're going to do. So there are, let's see, there's n total closings. So let's just draw the graph again. So after the first closing, instead of n barns that we have to visit n minus 1 barns, right? After the first closing, it's n minus 1. After the second visit, it's n minus 2, et cetera, right? That's the amount of barns that we have to visit after each closing. So after the first closing, 3, we have to visit n minus 1, which is 3. We're supposed to visit 3 total barns, right? And we're going to run a similar function. We're going to run DFS on node 1. And we're going to see that's going to go to 2, but it's not going to travel to 3 because it closed down. So that means that we only visited 2 total nodes, but we were supposed to visit 3. So since this is not matchup, we print no. So the way we know, the way we keep track of how we're going to, whether we can travel to a future node is we're just going to store it in like something like a visited array, right? We're just going to have a visited array and mark this as visited for like a separate visit array for like places that you cannot visit, basically. And there's also one more part of this problem. So hypothetically speaking, we've been closing off different barns, and we've been just starting a depth first search at node 1. But we wanted to know like where to start a depth first search, right? We have to know like a node that we can start a depth first search on, because what if they close off node 1? What if they close off barn 1? Then we couldn't DFS at node 1 anymore, right? So we have to know where we can go through. So basically, we're just going to loop through the array of the restrictions of where we can't visit, and then just find the first node that's available. And then we're going to start a depth first search on that, and we're going to be able to tell the graph is fully connected. So that's basically the idea behind the algorithm here. So let's go over the code. So again, the key idea is to identify data structures. This is always the case that in these USACO problems, identify what you can use, what type of problem it is, the data structuring algorithms to use, brainstorm that. Read in the input and make a DFS function. This is basically the essential driver of what's allowing us to figure out this problem here. So simulate what it says, and then basically what I said, find the starting node to DFS at, and keep an extra visit array to restrict which nodes to travel to. So first, we're going to define our inputs. We're going to make our graph, and we're going to create a visit array. And this is the extra visit array, which is going to be basically where we're going to store like the places that you cannot visit, the places that got closed. And finally, I'm going to keep a running variable of the visit count, which is the amount of nodes that have been visited each iteration. This is what we're going to do to check if the barn is fully connected. So here's our DFS function. I just cut it down in terms of lines, but it's the exact same thing. So basically more or less the same thing. So if we visited the starting node, if we visited the place we want to DFS at, then return. Or if we also visited a node that we're restricted from going to, also just ignore that because we can't travel there. Otherwise, we're going to say we visited the node there, and we're going to say visit count plus. That means we've been able to visit a new node. So we're going to increment the amount of nodes that we visited in this particular graph traversal. And then we're going to say for every node inside the edge, we're going to visit the new node, right? So this is everything here is basically your standard DFS function other than this part and this part, which is basically problem specific, where we just have to check if the barn we want to go to is restricted or not. And we have to check how many nodes we have to travel to. So that's why we're updating the extra the visit counter. So we're going to read in our input in the main function and make our graph using this for loop over here. So just make our adjacency list right here. It's going to fill this graph up with the nodes that are being read in as input. And the problem asked originally, is the graph fully connected? So at this point, I know that none of the nodes are closed down or restricted. So I'm just going to DFS at node 1 to make it simple, right? So I'm going to check if the amount of nodes that we visited from this DFS function is equal to n, which is how many nodes that it should visit. If so, it prints yes, otherwise it prints no, right? So that's the first step that we have to do. Then I'm going to reset my visit array, because notice that when we did our depth first search with node 1 as a starting node, it filled up the visit array. But I want to fill this back to everything being unvisited because we're starting over, right? Each iteration we have to start over. So I'm gonna reset visit count to be 0 because again we're starting a new iteration. So the amount of nodes that we visited is going to start off at 0. So I'm going to start off making another variable here, which is how many it should visit. So originally, if we close down one farm, it's n-1 nodes that we should visit. If we're closing down 2 farms, it's n-2 total barns that we have to visit. So since we're closing down our first farm in this iteration, the amount of nodes we should visit is n-1. And I'm going to decrement this after each iteration. So that's the reasoning behind that. We're going to loop through every time that we need to close a barn, read it in as input, and say extra visited at index B is equal to true. This means that we've added the restriction that we cannot visit node B. So when it runs this in the DFS function over here, an extra visited, it won't be able to travel to that node specifically at all, right? Because it's closed down. So I'm going to start off my starting node at -1, just set an arbitrary number to the starting node, and we're going to find our first the first node that we can DFS at, because like I said, you can't just DFS at node 1 every time, because what if they close node 1 first, right? And they could have closed the barn one at the first iteration, and you wouldn't be able to DFS at node 1. So you have to find the first node that you can start at. So I'm going to loop through the visited array, and if the node is also not visited inside the restrictions, then we can set it equal to that and just be done. We found our starting node. And next, we're going to DFS at that starting node that we just found. And again, just like how we printed yes, if all the barns are visited, we're going to do the exact same thing here. And then we're just going to reset the visit count equal to 0 because we want to prepare for the next iteration and make everything false again, right? And I already explained what should visit do. So that's basically going to do, after every iteration, we're going to find the first node that we can DFS at and just check if that is going to lead us to an answer in which the amount of barns that we should visit is equal to the amount of barns that we do visit using the DFS function. So that's the idea behind this problem for graphs.
Okay, so that's it for yesterday's homework. That involved the DFS algorithm that we went over yesterday. Now we're going to go over a whole new different topic. But first, I want to give us an intro to see what's the use of this topic that I'm going to explain, which is prefix sums. So let's look at the situation where we're given n integers and we have a few different queries, which are like, queries are like different problem. Let me try to explain this. So for each query, find the sum of a contiguous subsection of the array containing n integers from A to B. So basically, let's say we want to take the sum of a subsection, like from 0 to 1, -2 plus -3 equals -5. Like that's one query. Another potential query we could have for this problem is summing from 5 through 7, which is like 1 plus 5 plus -3, which it would be equal to 3. So basically, given n integers and we want to sum these two different queries, then we need to figure out how we would do this, right? Intuitively, based on what we've learned, how I would approach this is I would I know since we're given A to B, right? I now know my starting index and my ending index, and I can iterate through these with an O of n algorithm. So I just go from the starting point and then to the ending point and sum it all up. And then I have to do this q different times for each different query that I'm given. So for the explanation on code, we are given, I'm going to read in the numbers inside the n array. So that's all that's doing, that's creating that sequence. And then there's like q different queries, right? So there's q different pairs of A and B, which are the starting and ending points. So q different times, I'm going to have to sum from A to B, which is relative to O of n, because you're iterating over a set subset of an n array. So basically, I'm going from the starting position and then up and equal to the ending position, and I'm just adding to the current sum and then printing it out and then ending line. So I created the array at the beginning and then I'm processing it using a q times n algorithm. So as it states here, this is O of n times q. However, like what if n and q are really large? Like if I had to do like 10 to the 5th different queries, I had to do like that many different subsections and I'd do 10 to the 5th. That's the size of the array. Then if you multiply those are 10 to the 10th. So that's over the 5 times 10 to the 8th limit that USACO allows us. So we want to do better than that. And one way to fix this is with prefix sums.
Yeah, so that was our kind of problem statement to kind of get you thinking. So if we have an array, so like go back to the, yeah, basically over here, let's say we have this array over here that has n numbers inside the array. Let's just say the length of this array is n, right? And there are q total queries, and each query is going to basically give us 2 integers that, and it asks us to sum the range of the numbers in the array from between those 2 integers. So let's say a is equal to like 3 and like b is equal to 5, so something like that. So we might have like a is over here and b is over here, right? So we're going to sum the numbers in this range here. So 8 plus -1 plus 4 is 7 minus 4, 7 plus 4, which is 11. So we want to process that for q queries. That's just one query, but we want to do it for q total queries. So as Brian explained earlier, basically we're going through n integers, worst case, right? Time complexity means worst case. So O of n means worst case. So if we're going through like n integers every iteration, and we're processing q total queries, that's where we get n times q. And as Brandon said, this is too slow for USACO. When you get to like higher divisions or maybe even certain bronze problems, it's too slow because let's say there's 10 to the 5th total integers and 10 to the 5th total queries, and you're going to have to process 10 to the 10 total operations. And that's way too big for USACO. So this is how we're going to fix it with prefix sums. Wait, could you go back to the slide? Yeah, so here is our integer prefixes. We're going to create a new vector that's going to basically house the sums of the numbers inside this array. So we're going to start off with a placeholder of 0 just to create like convenient indexing, because usually like it gets confusing about like whether you start at index 0 or index 1, right? So I'm just going to put a placeholder here, but just ignore this. Just treat it as if it's not there. I'm just basically trying to make this array like clean to use. So essentially what's happening in this prefix array is I'm taking the elements and I'm summing the previous element to the next element in the array. So for example, I see 1 over here. 1 is the sum of 0 and this number over here. Now I'm going to go to the next number. So I see 6. 6 is the sum of 1 and 5, right? And I'm going to continue doing this. So 8 is going to be the sum of 6 and 2, et cetera, et cetera. I'm going to build this entire prefix array from beginning to end, right? So let me change my color again. So you can see that 1 plus 5 makes 6, 6 plus 2 makes 8, 8 plus 8 makes 16, 16 minus 1 is 15, plus 4 is 19, and just going to construct the entire array from beginning to end, okay? So I just want you guys to observe quick something that is important. So this is 0, this is 1, this is 1 plus 5, this is 1 plus 5 plus 2, right? So I'm basically, I'm just adding the next number to the iteration. I'm just building it from top to bottom, right? This next value is 1 plus 5 plus 2 plus 8. So you guys can kind of notice the pattern. I'm just building this line over here and I'm just adding one number to it, which is the next number in the iteration. So the pattern that we see is that if we want to subtract two numbers, like the numbers, we want to find the sum of a range, right? All we have to do is subtract two numbers. Let's say I want to find the sum of the numbers between indexes 1 and 3, where these like are the A and B values, right? Then all I have to do is get this sum and subtract this sum. So just manually looking at it, 5 plus 2 plus 8 is equal to 7 plus 8, right? 7 plus 8 is 15. So this is the sum that we want to get, right? I'll just say S. So S is equal to 15. So the way we're going to get the sum without having to loop through the entire array, loop through between A to B. Remember, this is what's causing O of N, right? So originally we have N times Q queries, N times Q operations.
Actually, like for prefix sums, you like subtract this.
Yeah, you have to do -1. I was going to explain that. Yeah.
Okay, sure.
So originally we have Q queries, and for each query, we have to loop through N total. We have to loop through N total numbers, right, in the array. But what prefix sums is going to basically allow us to do is change this to, instead of O of N times Q, change it to N plus Q. So basically what's going to happen here is instead of looping through each A and B, we're just going to subtract two values because we don't need to loop through the entire array anymore. We just have to do that one time, and then we're going to be able to construct this prefix array. And it's going to be able to solve our problem here. So let's see what's happening here. So I'm going to notice that 1 plus 5 plus 2 plus 8 over here is going to be our sum for this section for index 3, right? For prefix 3, and that's equal to 16. So the reason why I wrote out 1 plus 5 plus 2 plus 8 is I can show you the math. So 1 plus 2 plus 5 plus 8 is going to make us 16, right? And if I subtract the value over here, sorry, so if I want to go from A to B, then I have to subtract the previous value. So I'll just subtract this value, like the value before A. So I'm going to subtract the value A minus 1, and I'm going to get our sum. So if I just subtract 1 over here, then I'm going to get, this is going to be sum to 16 minus 1, that's equal to 15. So we've got our sum over here. So let me just briefly go over that again. So let's say we want to sum all numbers in this range over here as an example. This is a different range, but yeah. This is A and this is B. And similarly in this prefix array, this is A and this is B. And this is going to be A minus 1. So essentially, this is equal to 0. This is equal to 1. It's equal to 1 plus 5. This is equal to 1 plus 5 plus 2. This is 1 plus 5 plus 2 plus 8. And this is 1 plus 2 plus 5 plus 8 plus -1. Right? So these are the sums of the numbers in this range. So if I want to get the sum of numbers between 5 to -1, which is the between indexes A and B, what I'm going to do is I'm going to say the sum is equal to, instead of looping through between A and B, writing a for loop to sum all the integers between A and B, I'm going to say the sum is equal to prefixes at index B, which is this sum, minus prefixes of A minus 1. So that's going to give me, this is A, right? So at A minus 1, the sum is going to be here. So essentially, if I want to sum these numbers in nums, I'm going to get 5 plus 2 plus 8 plus -1. So 7 plus 8, 15 minus 1 is equal to 14. So that's the sum that we want to, right? So we use, that's like just normally iterating through the numbers, just adding them with the for loop. But instead, we can use this prefix array, which is faster. So we're going to say prefixes at index B, that's equal to, let's see, 15. And we're going to subtract prefixes of A minus 1. And prefixes at A minus 1 is right here, and it's equal to 1. So that's why we're going to get 14, and we got in the same sum over here. So basically what we're doing is we're just storing the numbers. So let me let you guys visualize this. So let me erase this quick. Essentially what's happening behind the scenes is we've gotten our sum of 14 as our answer, but how do we get there? So we're taking the prefixes at index B and we're subtracting the prefixes at index a minus 1. So we're going to say 1 plus 2 plus 5 plus 8 plus negative 1, right? That's basically what's happening here. And this is prefix index B. And we're going to subtract prefixes at a minus 1, which is 1. So in the end, this 1 is going to cancel with this one, and we're just going to get the sum of the numbers between that range. So that's why we're able to get the sum of the numbers in a range with prefix sums. So the benefit of having this algorithm is that it runs in O of n plus q time instead of n times q time. So if you're having that example again, where n is 10 to the 5th, and you're adding q, which is another 10 to the 5th, you're just going to get 2 times 10 to the 5th. And this is way less than when we did n times q, which is 10 to the power of 10, right? 2 times 10 to the 5th is much better than 10 to the power of 10. So you can see this algorithm, it runs much faster. So the reason why this algorithm runs in O of n plus q time is the reason here. If we're having this prefix array given, we need O of n time, we need n operations to create the prefix array, right? The prefix array is going to take n, we have to go through every element inside the numbers over here to generate this prefix array over here, right? And now that we have this prefix array, for every query, we just have to check at a specific index and subtract another index. So these are constant time. We're not going to have to multiply it by n times q, right? We're just going to go through each query, and each query is going to be instantly solved. And that's why we're adding q instead of timesing it by q. We're not looping through the entire array every single time we want to process a query. We're just going to subtract 2 indexes, and we're going to get our answer. So that's why prefix sums are so useful.
Yeah, basically like array index access is constant time. So that's why that's much faster, because you're just doing the summation all in one step rather than for each like query you're doing another summation. You're just doing that all in once and then doing constant time array access later. So that allows the n plus q. Okay, so this right here. Okay, is this just an example problem or?
So this is the same problem that we saw before, but instead of having to have this array and for each query loop through n elements, we're just going to subtract 2 numbers total, and it's going to run much faster. So instead of looping through the entire array, which is going to take a lot of time to sum up all the values, we're just going to subtract 2 values, and that's going to take like no time at all. So that's the idea behind this. So here is the implementation that we put for prefix sums. So I'm going to read in n and q. I'm going to have a prefix array over here. So n plus 1 elements, I'm going to store that placeholder of 0, if you guys remember that I told you guys to ignore. And I'm going to read in a number and as input, and I'm going to say the next element that I want to push inside this array is the previous number plus the input, right? So the previous number is going to represent the sum of all elements before it. And the number that we're going to input to the end of the prefix array is going to be the next number that we're reading as input. So we're going to push in the sum of the numbers. So after this, we've gone a prefix array instead of a normal array. And this is going to give us the ability to sum each element using this formula that I wrote over here. So we're going to, for each query between 0 and q, we're going to read in 2 numbers, a and b, and we want to find the sum of the numbers between a and b. So again, like let's just make an array here quick. So instead of having to loop through potentially, let's say worst case, right? In time complexity, we're considering worst case. Let me erase this. In time complexity, again, we're considering worst case, right? So let's say the worst case is a is equal to 1 and b is equal to n minus 1, right? Then we have to loop through n elements over here just for that one query. And then let's say that in the next case, a is equal to like 2, and there's like n minus 1 elements over here, and like let's say n is like a million, right? We don't want to loop through a million elements again because that's a waste of time. We don't want to do that for every single query because that's going to take like way too many operations. So instead, we're going to just use this formula after generating this prefix array, and we're going to use that formula to subtract the 2 sums from the prefix array to get the sum of the numbers in that range. And again, this is going to run an O of n plus q time because you can see that there are n operations that we have to perform to make this prefix array. And there's another Q operations that we have to make to answer the query. So it's O of n plus Q. So that's why prefix sums are so useful here.
Okay, so now we learned about prefix sums, but now let's go over 2D prefix sums, which is the same thing except for summing the elements of a 2D array. Now, okay, given this right here, we want to find the way to sum a section of a 2D array. So the summing of this section would be called a query. So each query contains 4 integers, which is the starting row, the ending row, which is like it says ensign row here, which is like, I guess that's another way to call it. And then starting column, and then ending column. So we're given these values, and given these values, we want to sum all the numbers inside this range. The way we would do this using like our understanding based on like using just normal for loops without prefix sums is we'd start from the starting row. We'd have an outer loop from like for int starting row, and then like as this value is less than the ending row, and then we just increment. Okay, so we'd have this as the outer one, and then in the inner row we'll have an iterator through the columns, starting column, and as long as it's less than the ending column, we're gonna plus. So what, and then we're just gonna print the numbers in each row. So basically what this is gonna do, it'll go here, then the column count will increment, then I'll take this one, it'll add this to the count, then this one, then this one, then this one, then this one, then the row is gonna increase, and I'll do the same thing. And I'll just go through every single element inside this box, and it's gonna sum it all up. So that's based on our iterative understanding of summing elements. However, we come across an issue. So we know that we can do this. However, the time complexity is not very good. It's n times m. For every single time that you sum, you're going to take, there's n columns and m rows. So as I just shown, that's n times m based on that nested for loop. However, on the outside of that for loop, there's Q queries. So we're going to have a different starting row, different ending row, different starting column, and different ending column for every query. So for every single one of those nested for loops, there's another for loop outside of those for every single different query that we want to process. So as you can imagine, this is going to be very time-consuming process. But let me just show what we're doing right here. So we're creating a bunch of rows, empty rows, and a bunch of empty, like a 2D array, because we have a vector that stores these empty vectors. So now we've created like a grid kind of shape using 2D vectors. And with this, we're just reading in input. So we're putting it into the desired slots. And then we want to sum based on like the x1, x2, which are like the given coordinates. So like here, like, let's say like we wanted to sum from like starting row is like 0, ending row is 2, starting column is 1, ending column is 2. Let's say that's our query. And then basically we're just iterating through it, and we're adding to our current sum. So it just +5, +6, +1, +7, you know, +5, +2. It would add it to the current sum, and then it would just print it out. And then for each query, we just read a different starting row, starting column. So we would just have different boxes. And for every single ending row, starting row, like all these different boxes, we'd have its individual summation. So as you can see here, this is a triple for loop with n times q, and that may not be that effective. And there's definitely better ways to do this. Okay, so our solution to this problem. We want to like build our prefix sum array first. Like, as you remember from like the 1D prefix array lecture, like we had like, if our initial array was this, we want to like sum it up. So we just get the summation of it, right? But we would also want to do the same thing for 2D. And then I want to show you guys, after I draw this out, I want to show you guys a visualization of how to do this in terms of 2D prefix arrays. So let me go to this website here. Okay, so basically, like what if this is the sum area that you want to take, right? If we did this iteratively, this would be q times n times m, as I mentioned before, because for each query, you'd have to iterate through the columns and the rows. But then since we learned 1D prefix arrays, one thought that might come to mind is we want to take the prefix sum for each individual row, 1D rows, right? As you can see, each row is like the sum of the previous, if you like compare this to this. So 1 plus 5 equals 6, 6 plus 6 equals 12, and then 12 plus 11 equals 23. See, like they summed it up. And then instead of iterating through each row, now we can actually do the B prefix B minus prefix A minus 1. And then that would give us the sum of this and this. And then all we'd have to do is iterate and then add up the results for each one. So instead of being q times n, now we have q times n, because for each query, we're just iterating down the rows instead of through the columns, because the columns have been pre-processed. However, we can actually still do better than this even. So that's just the first thought that comes to mind now that we know prefix sums for 1D arrays, but now we want to have a more elaborate 2D prefix sum process. So so as I mentioned before, you want to build the prefix sum array as we did for 1D arrays. We can build the 2D prefix sum array. Instead of summing the rows individually with multiple 1D prefix sum arrays, we can actually have a formula that I'll help you guys visualize. So the way you would build a prefix sum array would be like you would have to, given that you already have the prefix sum array of smaller elements, you can actually build that up and make a larger one. So let me try to visualize, like allow you to see this better. So in a prefix sum array, you want to leave the outside zeros as I did for the other one. And let's say that I want to calculate, let's say the current array looks like something like this. And then if I want to calculate prefix sum of 2, the prefix sum of 2, then I would have to do this area, add like I minus 1 j, and then I have to add this area. And then I'd have to add, okay, wait, the prefix sum hasn't been built yet, so I don't know what that is. And then I'd have to add the prefix sum of, I have to subtract this section because I added it twice. And then I'd have to additionally add an element here, right? So like, okay, this is hard to explain, but I'd have to add the array of 2, 2. So like basically, for the prefix sums, let me try to just show you guys this. So basically we'd have to add, okay, wait. So we want to add the previous prefix sum and then the one on top as well, and then subtract this overlapping area, and then just add the new element. And then that would allow us to build the current prefix sum value. But like this will probably be easier to understand when I show you guys the code. So like just keep that in mind. But basically you would just keep on iterating through the prefix sum array and then generating the new prefix sum element based on this formula right here. And once we have our whole thing built out, if we want to like calculate a specific sum for a specific box, then all we would need to do for that is use a separate formula. So we use this formula for creating our prefix sum initially. And now that we have our prefix sum built out and we want to get a specific rectangular box sum, like if I want to get this, for example, then for that specific sum, I would just do, I would get the, okay, wait, so I would basically, okay, I'm gonna draw the prefix sum array. So like now let's assume I built it out and I don't need to like build it anymore. Let's say like the prefix sum looks something like this. Like if this was what my box looked like, if I wanted to calculate the prefix sum at like 2, 3, then I would just do well, no, if I want to calculate the sum between A and B, then I would just do the total. Like if I wanted to calculate the sum of the array from the second, like, okay, wait, this is hard to explain. So if I wanted to get the sum of a certain box, like let's say in the original array, so this is the prefix sum array, the purple one that I'm describing here. And let's say that the original array looks something like this. Like, I don't know. I'm just gonna draw something out right here. So let's say this is the original array, and I just put some random numbers there. But if I want to calculate this sum right here, then in the prefix array, I would get the equivalent of this spot right here, and that would give me the sum of this entire thing. That's what that represents. And then I would do A minus 1 B, so that would be this, which represents this. So currently what I'm summing is, so currently what I have, so I basically, okay, wait, let me try to do it in different colors to make this more clear. So basically I added 7, and now I'm subtracting this, and then I'm subtracting this, and then adding this, and there's a reason why. So in terms of adding this is what I'm doing. Okay, this actually, okay, so this is, okay, let me restart this whole thing. This is the target sum, right? But in terms of the prefix sum, if I want to get this, I'll basically add the whole thing. That's what this represents right here. And then I'm going to subtract this element right here. And what that is, the equivalent of that on this board would be subtracting this whole section. So now there's none of that. And then I'm also going to subtract this section, which would be the equivalent of subtracting this part. But now you can see there's an overlap here. I subtracted twice, so I want to add that back. So if I add this from the prefix sum, that's the equivalent of adding this back. So effectively on the original array, I've added the whole thing by using these prefix sums. So this is really hard to, like, you have to really internalize this process. This is something that takes a lot of process to actually understand. But basically what I've done here is using the prefix sums, I've essentially added the whole range of the numbers that I desired, which is this section right here. So yeah, that's really hard to explain, but hopefully like when I show you guys the code, you'll get it better. And you should definitely review some of it on your own time. So there's 2 parts to this. The first part is generating the prefix sum array using the formula that I've described before. Based on the previous prefix sum elements, we want to generate the new ones. And we keep on doing this. So we start from the bottom, the 0, 0 prefix sum, and then we keep on like increasing. So like what this is describing right here is we have like a bunch of zeros, and then like let's say I want to calculate prefix matrix 1, 1. So basically I would add our existing elements here, subtract the overlap, and then I'd add from the other array, so the original array. So this is the prefix array, right? Then I'd add the equivalent spots in the original array, whatever that is, and then add it, and then I'd create the element here. And then if I want to create 1, 2, then I would have to, based on the previous prefix sum elements, which is this, subtract the overlap because I did it too many times, and then I'd add whatever element is in this box and put it here. So then basically if this is 2, this would be 3 because I have to add everything from the previous and then add the array here. So basically iterating through every single step of the way, I'd eventually generate an entire prefix sum box based on the previous prefix sums elements and then the array elements. from the original array. And then once I have the whole prefix sum built up, then I can process my queries. So creating the prefix sum array in the first place takes n times m time. And so this took n times m time because I was processing through the entire prefix sum array, and then I was also I had to go through all the rows and columns to generate the entire prefix sum array. But now since I've generated the sums completely, I can use simple like constant time access formula in order to print out the box that I want. So for instance, if I wanted to print out the sum from like if I just wanted to print out this sum from here, like if I specified this as the parameters, all I would need to do is add this, subtract this. Okay, wait. So if I wanted to get the sum of the original array, the original array is like 2 and like 4. Like let's say that was if I wanted to get this sum, in terms of calculating that in the prefix sum array, I would basically be just adding this, subtracting this, and then adding this, and eventually that would lead me to what this is right here. So yeah, that's basically the explanation of 2D prefix sum summation. It's might be a little hard to visualize, but once you get used to it, you'll definitely understand that. Okay. So now there's gonna be an example problem of regular prefix sums here.
Yeah, so Brandon, you can give them a couple of minutes to kind of like read the problem before you go into the solution.
Yeah, I'll just let you guys read this one.
All right, so I guess we can kind of go into the solution here. So essentially what's happening, out of the interest of time, I'll go a little faster, but essentially what's happening is it's giving us 1s, 2s, and 3s over here. Let's read the problem. So Farmer John's N cows conveniently numbered 1 through N are standing in a row. And each row has an ID. Farmer John would like you to help count the number of cows each breed has within certain intervals of ordering. So it gives you N and Q. You could see that this is 10 to the power of 5, right? So we obviously, like this is hinting at how earlier when we were talking about the time complexity, we can't do 10 to the 5th times 10 to the 5th because that's equal to 10 to the 10th, which is too many operations for YCPB. You're not going to have enough time to be able to have your code's not going to run fast enough to be able to answer each query in O of n times Q times. So we have to have an O of n plus Q solution, right? O of n plus Q. So here is what we're going to do. So it's going to give you the breed ID in each ordering, and it's going to ask for the amount of, so there's 3 types of cows. There's Holsteins, I'll just represent that with H. There's Guernseys, G, and Jerseys, J. And it's going to ask us to sum the amount of each type of cow in each range, right? So like, let's say this is like 1, 2, 3, 4, 5, like these are columns, let's say. So it's going to tell us that we're going to start off with like 2, for example. So I'm going to put a 2 here and kind of build this like visualization for you guys. So 1, 1, etc., etc. So basically, it's just going to give you the cows in order. And we're going to have to print out the amount of each type of cow between A and B for like Q queries, right? So this is kind of like the same thing as what we've been doing this entire time, prefix sums. So let's look at the code quick. So here we're going to read our input and construct 3 prefix arrays, right? So because originally we only had 1 prefix array for our first problem, but here we have to print out how many H's, G's, and J's are between each range, right? We have to do that for every single type of cow. So that's why I have 3 prefix arrays instead of 1, but essentially it's the same concept. So I'm going to read in a number, the cow, and I'm going to say if the cow is equal to 1, which is like in the problem, it says if it's equal to 1, then it's a H type cow. So we're just going to increment like the amount of cows that are at this point. And since there's no like G or J cows that are incremented at this index, then we're just going to add the previous number from there and add it on to the next value. We're going to do the same thing for 2 and 3. It's just going to be the type of cow that's being read in this input is going to increase its value inside the prefix array, right? The other ones remain unchanged because that cow isn't being added at that certain point. So next, we're going to go through our Q queries over here. And you can see that it's pretty simple. We just have to have our integer A and B, which is the beginning and ending of our range of numbers that we have to, the range of the number of cows that are in that array, like inside the prefix array. And we're just gonna print using the formula for the prefix array, prefix of B minus prefix of A minus 1 is going to give us the number of cows in that range. And we're going to do that for H, G, and B and just print it out. And that's basically our answer. So pretty straightforward. It's basically just the exact same problem as like the ones that we described earlier when we were introducing prefix sums. But yeah. So next I'll let Brendan cover a second example.
Yeah. Okay, now I'll cover this is another problem dealing with prefix sums. So let's see, I'll give you guys like 30 seconds maybe to read this one, process it. I'll explain the problem and then I'll go over the solution. Okay, so I feel like I've given you guys a while to think about this. So a couple things to note in this problem. There are many approaches, but you are limited in your approach due to this number right here, which is 10 to the power of 5. So we've seen this 10 to the 5 power before. I feel like we've shown you n times q. If you do like n times q of 10 to the 5, you're not going to go under the time complexity based on our previous concept that we've shown before. So I feel like this might have to do with like prefix sums possibly, but let's read. So it's okay. So there's some signals that have gone down, and given a list of these damaged signals, we have to see how many we have to repair in order to have a contiguous block of at least k working signals. So we want to replace signals on a block so that we have k signals in a row that are working. So currently we know, let me just draw the thing out real quick. So according to this example, we have 10 total 10 total crosswalks. And then the second number, it seems like k is the amount of broken signals, but then okay, b is the amount of broken signals, but 6k is the number of signals we want in a row to be working. So it tells us that there's 5 broken signals b. So we know that basically that we'll see on the next 5 b lines that 2 is a broken signal. So I'll mark that as a broken signal. This is a broken signal. Actually, I should write it like this just to make it clear. So whenever it's a broken signal, I'll just mark it as 0. So this is a broken signal, this is a broken signal, this is a broken signal, and this is a broken signal. Everything else is fine. So one way you could do this problem is you loop through every single range of k, which in this case is 6, and then sum it up. Okay, so I sum this up and it looks like it's 3. And since our target sum is to have 6 in a row, we'd have to repair 3 here. So our running minimum is 3 signals that we have to repair. Okay, let's look at this range. It looks like there's 4, this adds up to 4. So we'd have to repair 2 zeros. So it looks like our running minimum is 2. Now let's look at the next range. Okay, so we're gonna go from 8 to 3. And then we see that there's only 1 0 in this range, and the sum is 5. So that means that's 1 less than our total 6. So our running minimum is 1 that we have to repair because there's only 1 0 in this range. And we're going to keep on going on the rest of the intervals, but we're going to see that no matter what range we choose, 1 is the minimum for the difference. And one way you could do this iteratively, or the naive solution, would be, okay, 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay, and then k minus the sum gives us the minimum for this query. And then we could do the minimum for this query, which is 2, like the value at 2, then 3, then 4, and then all the way. So for each interval, we just add up, and then we see the difference between the current sum and then the k value. And then if that's less than our current minimum, we update. That's the naive solution. And the time complexity of this solution is n because we have to iterate through an n-sized array, even if it's only we're iterating through an n-sized array. So worst case, like this is equivalent to an n algorithm. If we have n-sized if we have like an n-sized n-sized row interval, like that would be worst case n, and then multiply that by n relative to n queries, because we're doing n around relative to n operations, because we have to increase our starting index until we reach n. So basically we're summing, the summation of our specific interval is relative to n, and then the increasing of our index is also relative to n. So this goes over the 5 times 10 to the 8 bounds that we want to establish for our problems. So it looks like we need to use prefix sums to improve this process, because what we could do instead of this is we could just sum up our current, we could do the prefix sum for this, which would look like this. Let me just erase this right here. We could generate a prefix sum for this row. And then instead of doing that, we could have this out. And now we can just take the separate prefix sums that represent a 6 interval block. and then we get the sum. So from if our k is currently 6, we want to add from we want to subtract this minus this in order to get our interval, the sum for that interval. So in this case, our interval sum is 4. So since k is 6, we do 6 minus 4, and that gives us 2 as the running minimum. And as you can see, even though we're iterating through, like, even though we're trying to calculate a sum of like this 6 right here, we're doing from 6. We have to sum further than that. We have to do b minus a minus 1. Prefix of b minus prefix of a minus 1. So if you want to calculate the sum from 1 through 6, we'd have to take the sum of the 6th elements minus the a minus 1 element, which is 0. So that means that in this interval, we have a sum of 3. And as shown here in the actual array, it actually is 3. So basically, instead of doing the iterative solution, we do a prefix sum solution. And then for each range, we'd subtract the things. And then for the minimum, it would be 5 minus 0, this range. And that would give us 5. 6 minus 5 is 1. So that's basically, we would just generate the prefix sums and calculate the current running minimum. And let me just go through the code really quickly. So basically, we're generating the prefix sum. We're generating the original array right here. So we're marking the 0, then like 1, like let's say like this is a 1, like, and you remember how like the last elements was valid. So basically for each index that's broken, we're gonna mark it with a 0. And for each element that's not broken, we're gonna mark it with a 1. And then what we're doing here is we're turning this original array to a prefix array.
It's the other way, right?
No, like the first one is just turning the array, and then this is turning the prefix.
For this code, I mean, like, we're having the opposite. So basically, like, let me just give a quick tip of advice to you guys. So when you guys are doing prefix sum related problems, observe what you're doing the prefix sum on. So originally, like, our problem when we're like showing the concept of prefix sums, we're showing the numbers in a range. So when you're doing USACO problems for prefix sums, always ask yourself what the prefix sum represents. So here, for this problem specifically, we want like the prefix sum to represent the amount of broken lights in a certain range, right? If we have the amount of broken lights in a certain range, then we can just find out how many we want to fix in order to get like the answer, right? So like, for example, here, we're going to have n crosswalks and we're going to read in the broken lights that are over here. And we're just going to say, generate the prefix array. So we're going to say the amount of crosswalks at that specific broken light is going to be incremented by 1. So that means that's how we're going to tell if there's a light there, right? So if there's nothing there, that means that it was never broken. But if there was a broken light there, we just have a 1 over there. So then that's where we're going to go off with our like prefix array here, right? So Brian, you can finish off now.
Yeah. Okay. So basically that now that we've marked, so it was the other way around. So basically, whenever you have an actual broken area, you want to mark it with a 1. And whenever it's not broken, we mark it with a 0. So now that we have these positions marked out, we want to create the prefix sum. So whenever we have a broken light, we want to mark that with a 1. And then, like, let's say this is the prefix sum. Then our actual prefix array would look like this. So now that we have our prefix array built out, we want to generate the running minimum, which is like right here. Answer represents the running minimum, and you want to initially set it to the max integer, so like it can be replaced later on with the actual minimum. So we'll generate through all possible k intervals, and then we'll get the sum of that interval using our original formula, which is b minus a minus 1, which is shown right here. And then we'll actually, once we have this, we want to see if our current answer, like our current sum, is if k minus that is less than the current answer. And if it is, then we're going to replace the answer with we're going to replace this we want to check if the amount of broken lights in our current interval is less than the currents. And if it is, then we replace it because we want to have the least amount of broken lights in our current interval. So basically what this does is it sums the number of broken lights, which are represented by the ones. And if that's less than our current answer, we'll replace it. And at the end, we're just gonna we're gonna print out our answer if it's less than 0, because we don't want to have a negative number. And that's basically should be it. So yeah. Okay, so now we just have today's homework, which goes over this prefix sum, which is important to practice on your own. We have a practice problem here, which might be easier, and then one that might be a little more challenging. Okay, so that's it for today. Thank you guys for coming. And yeah, tomorrow's topic, we'll be going over a different concept, which is binary search, which is extremely important. So hope you guys come for that one. And see you guys tomorrow.
Thank you.